I will officially start the lecture so today's lecture within the lecture series on sustainability in computer science. I'm very happy to welcome Professor Wilfried Elmenreich from the Alpen-Adria University Klagenfurt. I really have to say I'm especially happy to have you also on board, Wilfried. I did a little data analysis after our last year's lecture. And when I say, okay, TU Wien had most of the certificates, okay, that's not difficult since we have most of the students, but Alpen-Adria University scored second. Yeah? And knowing that you don't have as many students, this means that it is really a topic at your university, and I know you have it in your development plan of the university, sustainability, and I think especially you are kind of one of the spokespersons also to this topic. Great to have you here, and we are very much looking forward to your presentation. It's your floor, Wilfried.
Thank you very much for the introduction, and it's great to hear that our students are quite motivated to take the course. This was also my impression last time. So I hope it's the same with this iteration as well. Okay, but let's get right onto the thing and start with the content. So I'm going to talk about electric load disaggregation as a means for increasing energy awareness and hopefully decreasing energy use. So, and I will talk about this possibility and how it works and what we would have to do to use it. So, stating the obvious, so we are using energy in various forms, and typically we have the problem that we are not so much aware of how much energy is used in what things, and probably we know that we have a lot of devices, but we are not aware of the particular energy consumption of these devices. And consuming energy, especially when not produced from renewable sources, is a problem, so we should reduce it. And even if we get it from renewable sources, probably we should know which devices consume a significant amount of power so that we can adjust to the times when renewable energy is available, so which is also a big topic in the grid. And the question is, what can a computer scientist do? Because this sounds like a problem for a power engineer or for an electric engineer, like doing measurements or doing stuff. Whereas the computer science, the computer or the programming problem there that can be solved in order to come up with a part of the solution. And in this talk, I describe how this question can be addressed. And we are going to use computers, smart meters, algorithms, and data sets in this talk. So all the things. So smart meter rollout, just a couple of weeks ago, it was again in the news that smart meter rollout in Austria is now more or less complete. So the EU Energy Directive that stems already from 2006, 2009, that stated we want to have 80% of smart meters in place for electricity consumers by end of 2020. This just, we were a little bit late, so it was finished now, 4 years late. I found it funny that in the explanation, they stated that COVID basically made it difficult to reach this goal, which is interesting because COVID reached us by early 2020. So there is not much overlap between the pandemic and the work on the smart meter rollout. But that's fine. Now we have the smart meters, and the question is, what can we do with this information? So now we have meters everywhere. So just show a picture here. So we have replaced one type of meter by another type of meter. And now we have a digital display. But apart from this optical thing, what are the possibilities that give smart meters to us in order to do something positive for energy consumption. So you're reducing it or becoming aware of it. And it has to do with how we can connect events to actually their causes. So the problem is when we get an energy bill after 1 year, which is typically the case. So we get our billing typically after, much later than the consumption occurred. Sometimes there is even an estimated bill which you pay, which is corrected afterwards, which is typical for Austria. And this means that the amount of money you pay for your energy is not very much connected to the amount of energy you have consumed in that month or even that year, because there might be a correction after this year and it would be changed for the next year. So basically we have no clue on how the energy was used that we paid for, because after 1 year I cannot remember what I did in overall half when I used a particular device. And if we would know if we would have this information, we would know which devices have used what time, then we could decrease our energy consumption, because we would use those devices that require a lot of power and that consume a lot of energy. We would use them more carefully. And the question is, okay, but why do we need to know this? Could we just save in general, trying to use all the devices carefully? In theory, yes, but that basically might cause you, don't know, for example, running around the house and turning off lights. But if your lights are powered by LEDs, then having one light bulb being on a minute more or less doesn't make a significant difference. While another device that probably while you were running around and turning off all the lights not needed, your computer probably was on. And as Professor Kappel already said in the introduction, having my video on and probably also with this background enhancement or de-enhancement, this is something that requires energy, that generates additional CO2. So if my computer is on and I'm optimizing the lighting, it is counterproductive, because I should have had a look on the computer usage first. So having this information is crucial. And there is a study that is analyzing this, showing different potentials depending on how detailed your information is. So if you just would have a little bit more information on your bill, this would already help. If there would be audits, if you would get feedback daily, if you would get feedback in real time, if you would get feedback on an appliance level. So if a system would tell you which device consumed how much energy that time. And then there is the idea of having something tailored to appliance level, counseling you, which depends on applications. But there is the expectation that this could even exceed 12%. So these are just rough numbers. I would take them with a grain of salt. So don't learn the numbers by heart, but just general idea. The more information we have, the better we are able to reduce our energy consumption. And so we have this information now from the smart meters. And the smart meter gives the utility company or whoever has the data and a timeline of the energy consumption, which is shown here. So this is a possible timeline. In reality, they will look a little bit more noisy, but just a general idea, this could be a possible timeline. And then the idea of load disaggregation is that by having some knowledge about the consumption patterns of different devices, so for example, a fridge likely has a consumption pattern that is like no or very low power for most of the time, then having a time where the compressor works because the fridge has to cool. Then inside the fridge, it is cool enough, so we don't have to run the compressor all the time. It is off for some time, and after some time it starts again. And if the fridge is closed and there are there's no new warm food put in for some time, then basically this would be a very regular pattern. And here, for example, this is an oven that was turned on to reach some target heat. So at the beginning, it's going with full power for some time until it reaches the target heat. And then we have the same situation as above. Just instead of cooling, we have a heating cycle. So we are turning off heating, then we reach a lower threshold for the temperature, turn on heating again, on, off, on, off, on, off. And this is what an oven would do. And here is the washing machine. This is a very simplified model because actually a washing machine doesn't heat all the time. But if it would be water heating for some time, it would be patterned like this. And this should be more diversified because we would have times where only the motor runs, times where it's even waiting so that the lingerie gets soaked. And then there is times when the water is heated up. So this needs to be sophisticated, but it is a pattern. So we will have patterns, and then this overall measurement sequence contains all the patterns. So in this case, we can identify, with a little bit fantasy, all those 3 devices. Of course, this has to work on a real system. So how does it look for a real measured power draw? So a little bit more noisy, as I indicated, but still there are significant features in that curve that are not purely random. So there is likely some information covered here in this, or contained here in this power draw. And can we disaggregate power draws? And this is what non-intrusive load monitoring is doing. So non-intrusive load monitoring is basically a decoding of these appliances that make up the total power consumption back into the devices. So here is another example, basically showing the same thing, just I colored it so that you can see where the different signal parts would end up. And you see that it's not so straightforward. Because, for example, if there is some power consumption, a signal that is first observed here suddenly is transposed up there and then continues back there and then is transposed up again. So tracing the blue refrigerator signal is difficult if you look at the absolute levels. So we would have to look at changes in the power draw in order to find those, which is already the first step for the algorithm. So in this non-intrusive load monitoring, we have a meter that does a central metering. And non-intrusive means that I don't have to install meters all over the place. So I'm not adding an extra meter to the fridge and an extra meter to the washing machine and an extra meter to every device that is bought new. Instead, I have one central point of measurement. And from this one central point of measurement, I get this power draw. And then I run an algorithm that is trying to disaggregate this information into devices. And this idea is not really new. So it was there long before smart metering. There was a suggestion of such an algorithm, including an algorithm given by George Hart in 1989. There were some follow-up papers on this that showed a little bit more sophisticated algorithms on this, also by George Hart in the 1990s. So long before we had the smart meters installed, long before the topic of renewables and energy consumption was really emerging, already there was an idea for such an algorithm. But now with the smart meters installed, there is renewed interest in what we can do. And the question is, what would be a suitable algorithm? And as a first idea, you could model it as a knapsack problem. So probably we had some, in some computer science lecture, you might have heard about the knapsack problem. So it's basically you have a knapsack, you have components that can fit into each with a different size or weight or however you phrase it. In our case, it is we have a maximum amount of energy and we want to find out which devices can make up this, this energy level. So we are trying to stuff as many devices into it as possible. So basically we take one snapshot from the power draw. So if we have, let's take this power draw, any curve would do. So if we have this draw, we would take one snapshot, and this gives us one power measurement. And saying at this time, the measurement was, I don't know, 3,231 watts. And then we have information about the power draw of the fridge, power draw of the stove, the power draw of the washing machine, and some other devices. And then we look which power draws could make up these devices. And this is a possible algorithm, but it doesn't work so well. So the problems we have with this algorithm is first, we have a considerable large search space. So if we have a lot of power draws to handle, if we have a lot of devices, then especially with the number of devices, it does not scale well. So we would require some heuristic search algorithms, but that's not a big problem because we don't need to get the absolute exact result because anyway, it's not guaranteed that that the knapsack solution is the real solution because they have the problem that the power of the devices is the nominal power, and probably if the real power of the fridge is like a couple of watts below, let's go for the good case, then another light bulb also might fit in, and the system might report that the fridge and the light was on, but it was just the fridge, or vice versa. Main problem is we have a lot of ambiguous combinations. So if we have devices with similar power, it's very likely that we would mistake one device for another one. And if we have a small change in power, so if we disaggregate for one moment and then we take the next instant and we do disaggregation again, we could have totally different result. So the first one would say that the coffee machine was on, and the second would say that the coffee machine was off after a second. And the second later, it would say the coffee machine is on again, which is very unlikely that we switch on off our coffee machines from second to second. And therefore it works only for a low number of devices, and it has its perks. Nevertheless, it has been done. There were experiments using data sets where we had the aggregated measurement of the power consumption of a household, and we had the disaggregated one. So we knew from a number of devices their exact power consumption. So in order to get such a data set, it's necessary to do an intrusive measurement. But once you have the data set, you can use it for training your and testing your algorithms. And the question, how well does it work? So here is one comparison showing on the right side the reality. It's just the amount of, this is the aggregated amount of usage of a device. And this is a case where it worked considerably well. Also, you see that some of the devices, for example, this dark gray device here was almost or not at all used in the real case. And this basically was imagined by the algorithm. And when we now think about what makes it difficult to disaggregate a system, is it the sheer number of devices, or is it the amount of power, which also play a role? But one thing to define appliance set complexity is also the similarity of devices. So if I have two devices that exactly behave the same way, so consuming the same amount of power for the same amount of time, I have a problem because I cannot distinguish them from the power draw. And also if I have, especially for this knapsack problem, the appliance set complexity is high if I have two devices that added up can mimic the power draw of another device. And to make things a little bit more interesting, or worse, or complicated, we also have to consider that a measurement is never exact. So we will always have some uncertainty around the measurement, and probably even for the not only measurement uncertainty, but also system uncertainty. So if you have a device that's with a nominal power consumption of 300 watts, we have to assume that probably the power consumption is not always to the point 300, but is around 300 with some system uncertainty around this. So we have some uncertainty in the system and some uncertainty in measurements. And if you would model this, let's say we are going to use some distribution, could be normal distribution, if we have no further information and assume that everything is independent. But then if we add up different ones, yeah, it's still possible to get a normal distribution from adding up two measurements. Then we can look into our appliance set and identify areas where the distributions overlap. If there is an overlap, this means this power draw can be produced by more than one combination of possible devices. And the more overlaps there are in an appliance set, the higher the complexity of the appliance set. So we get an appliance set complexity. And also, if we look at the devices, if we only look at the devices that are currently on, we can also define this complexity as a property over time, because we could have, for example, here we have low power consumption, but we have some complexity that is non-zero. So here we're close to zero. Why? Because we might have many small devices that can define it. And then here I have some other power draws. So complexity could even go down a bit. And then in general, if we have a lot of power consumption from different devices, then complexity goes up. So we have different complexity, and this complexity is more or less an indicator how well we would be able to disaggregate, especially if you use a knapsack approach. Okay, but back to the example with the coffee machine. If we have the hypothesis about the disaggregated set at some point of time, then we can assume that the state in the next time instant would be depending on this. So there is probably some correlation between one state to the next state, because it's unlikely that all the devices get switched from one instant to the next instant. And so it would make sense to apply something like a Markov model. So a Markov model, if we only look at one process, would be a system where we assume that the state can change with a certain probability, which basically would work unless we have additional information. If we don't have information, we can just assume that, for example, a device would have two states, so an on state or an off state. In the on state, it would consume a certain amount of power. In the off state, it would consume hopefully 0 watts, but there could be also cases where we have standby power. So this could be also non-zero, but if we assume that we have two states, then there is a certain probability to move from one state to the other state. Like there's a probability to, I don't know, turn on the television. And then there's a probability to stay in the state or to go back to the off state. Some devices have multiple levels, so we can have different power draws. And if we take this as an appliance model, so if we use this Markov model, and then we get like different Markov models. But the problem is what we observe is the overall power consumption. So we cannot correct our observation based on our measurement. We only have the overall measurement, but factors of this measurement will follow, according to our assumption, a Markov model, which gives us a factorial hidden Markov model. And we can use this in order to try to solve this aggregated power load, the disaggregation of this. And this is an approach that works much better than the knapsack problem. Still, it is quite resource intensive for doing the calculations because you have rather a complex problem. So it's interesting from a point of view how you solve it. For example, in some research work we have done, this was done with a particle filter optimization. So we used the heuristic optimization in order to find a solution for the disaggregation. And we did this, and you see here on the bottom, there is the publication, and you see also here the date, 2015. So what happened after that? So after that, there was something that really changed all approaches regarding load disaggregation, because then there was the advent of the deep learning approaches that came, which basically are black box solvers where you can give them a problem. So in our case, it's basically a classification problem. So we have different devices and we have this input, and we have the hypothesis that in this input, which is the power draw, is the information contained which devices are on or off, and we should do classification of the proper devices. And in order to use a deep learning model, so deep learning just means that we have a neural network, and with multiple layers. So in theory, a neural network with one hidden layer would be already sufficient to map every possible function. But with deep learning, basically it was found out that by using many different hidden layers, it is easier to come up with, to learn or to solve a given problem based on an example given. So what we need is we need a reference. So we need this data set again. And this time, not only for checking if our results are correct, but we also need this data set, in this case, for training. So part of the data set will be used for training. And input to the algorithm is a sequence of previously measured power. Again, here we have to think, how much input do we want to give the algorithm? We don't want to feed the algorithm with the 86,000 data points of one whole day, because that might be, if we measure once per second, this would be probably too much. So we have to consider, is it sufficient to look at the last 10 seconds or at the last minute? Or should we have a higher measurement frequency and just look at 1 second? So the modeling of the input data is one thing. Then, since we know which devices have been on or off during this time, we can then train a classifier using machine learning. And then we get a black box system that takes as input a data sequence, and as output, we get a classification. And it actually works quite well. So compared to the results of previous algorithms that have been published in the area of load disaggregation, the deep learning approaches really excel. The problem is it is a black box model, so we don't know exactly how it is done, and there are still some open questions. For example, if you want to use this at your home, you say, this is a great algorithm, and I know how to get the measurement data. So if this problem is solved, all I need to do is like to hook up my Raspberry Pi to this and then run the algorithm and have a display that shows me which devices are on. Let's do this. But the problem is that for the training, you need a data set. You need to have a data set, preferably of a target system, where you have measured the different devices. So first you have to do an intrusive measurement in order to do a non-intrusive measurement afterwards. You would have to do retraining whenever you get a new device. So that is rather not feasible. So the next question that arises is, okay, now we are going to use a data set. We try to train a load disaggregation algorithm for one data set, and we can test it with the parts of the data set that have been not used for training. And we can look at the results and we can classify it. So here on the right side, you see some results where different classifiers have been tested in order to find out how well we can detect a number of appliances. So in this case, it was a fan, hairdryer, a lamp, vacuum cleaner, and a kettle. And we see here the scores for matching them. So the hairdryer was easy to detect since it had a significant amount of power. So there was a high rate. And here the first algorithm here, the nearest neighbors, k-nearest neighbors classifier is quite good. If you look at the last algorithm, logistic regression, so we see here that, for example, for the fan, we get a 0.5, which is basically just throwing a coin in order to guess if it's currently on or not. So, but in general, we get appropriate results, but we have to come up with some solution to like train the model in general, and then probably use it in another context. So the transferability of these approaches are still an open question. So research to be done here is first on modeling the system, especially with the input data, how you represent it. You can also think of feeding it either with the direct power values or probably taking the power values and on a logarithmic scale. Then the addition of power values does not work anymore, but there is a better expression of the different scalings. So smaller devices then would be more significant. So there are some possibilities in the modeling of the approach. There are some possibilities in doing research, how well you can transfer those results to some other system that is unseen. So doing it on unseen data and running it on unseen data is the key question here. And then, of course, what would be the steps to set this up, especially if we want to test different things. And even more important, we have this challenge that if we now implement something, we would like to know how does it perform in comparison to other implementations already. And there is an interesting software project, NilmDK, which is an open source software project. It was used a lot back in the time when it came out. Nowadays, it's not used so much anymore because of some issues with with keeping up with the newer requirements, and therefore there is a derivation of this, which is the deep NilmDK system, which is basically driven by Hafsa Busbiar and Anthony Faustin. And you can find their implementation explained in a paper. And the real idea is that there is a standardized evaluation framework. So with fixed preprocessing and feature generation steps. What is typical preprocessing for data? When you get a measured data set, you would expect that it has nominal measurement frequency, and then you get a value for each time instant, right? And in reality, it frequently happens that there is some outage of the sensor, that the sensor has to be restarted, so that some data is missing. So we constantly feature the problem that we have data sets where measurements are missing, or some measurements are obviously off. So stuck at errors, getting sometimes 0 as a measurement. Also, this is unlikely in a system large enough where always some consumption is taking place, or getting a measurement that is maximum, which is also more likely an error than the actual measurement. So those things have to be processed. And so this is what is done, the pre-processing, feature generation, typically identifying changes in the power consumption. So there is a lot of pre-processing that really influences the quality of the result until you actually feed it into some trained system, or into a training system, in order to get disaggregation of your devices. So these are some of the challenges on the technical end. And then there are other challenges which are more on the user side, which are also very interesting from a computer science point of view. For example, there is the question, so the machine learning algorithm that is done, for example, with any algorithm. In NimPK also have predefined algorithms to test this. They give you a vector of devices, and you can look which devices are on or off at some time. There is a good match to the real devices. But what is not done, because the system doesn't have the information, is to do the labeling of the devices. So we need to find out which devices are corresponding to which events, to which on-off things. And for example, here is rather a simple power draw, because it's reduced to few devices. But you see here that we see here a peak from a fridge that should reappear periodically. Okay, this is a very expanded timeline. So this is only 25 minutes. So probably the fridge is on 3 times here. Yeah. Then we have here a microwave that is used, then going off. So here we see the cooling fan still running for some time. Then here we see could be computer screen, could be a TV screen. We see a water kettle being on. We see a dip also from the fridge. Water kettle events, fan, and fan again. And one question is how this can be done by doing the labeling. Of course, one possibility would be to show just or to ask the user all the time, but that would be a lot of asking and a lot of re-asking. And another possibility would be to use information, what we know about behavior of fridges, probably what we know from other measurements, or what we get from additional input in order to try to do the labeling. So this is an interesting problem. And this is something, because I talked about machine learning, and machine learning is also frequently used with AI in the same sentence. But nowadays, when we speak of AI, everybody thinks of large language models. Everybody thinks of the things like ChatGPT, where you can enter something and then there is some kind of natural language processing and reasoning at that level. And those things are not good for doing the disaggregation of data because they are not good with numbers. They are not good with data. You can easily convince them that 2 + 2 is 5. But if you need to do some deducing of finding out which device that could be. For example, there is a device that was running in the morning with roughly 1,100 watts for 1 minute. And this device is used once or twice, like every day. What could that be? Could it be the microwave? That somebody's using the microwave every day in the morning? Could be, but more likely is a coffee machine, especially if one is like a heavy coffee drinker like I am. So this kind of reasoning, that could be supported by large language models, and there you could draw the loop also to language processing and AI that is so much talked about and also used nowadays. So there might be the problem of labeling, the problem of the data processing. And one thing I didn't talk much about so far was how to get the data. Because I think that was clear from the beginning, right? We all have now smart meters, and therefore getting the data should be no problem at all. The reality is somewhere off from that, because the smart meters, they are designed to replace our meters, and the previous meters had one job: to provide the overall energy consumption to be used for billing. So it was very important that they did a very accurate measuring of energy consumption, but it was not so much important to like produce frequent measurements for feedback or so. And typically a smart meter is a bit flexible in this, and it does a lot of measurements per second in order to properly calculate the amount of energy that is consumed. But the interface of the smart meter to the utility company gives us values every 15 minutes, and this is already the opt-in case. In many cases, it's measuring it every hour or even less than that. And if you look at this timeline here, at this power draw, you see that within 15 minutes, that would be from here to there, a lot of things can happen. A lot of devices go on off within this duration. So we would entirely miss the usage of the microwave here because it is totally enclosed within this 15 minutes. So with 15 minutes interval, we don't get enough information to be able to analyze this power draw. And with 1 hour, also not. There is, however, still some information you can get from a 15 minutes interval or a 1 hour interval, which is the overall power consumption of a household. And actually, this is a privacy concern because it gives an information, or at least an indication, if somebody is currently at home, because when we are at home, then we're using devices, we're turning on the television, we're turning on the computer. So the power draw is much higher when we are home than when we are not. And so there might be information about the daily routines of a person by analyzing their power draw at 15-minute intervals. So there is this privacy problem. So the privacy problem doesn't go away with 15-minute intervals, but there is also the problem that it's not enough to get enough measurement points for doing a proper load disaggregation. So we have another problem. We have to solve the problem of measuring our data, since it's not done by the smart meter for us with a sufficient frequency. And this brings us to private smart metering. So it is allowed and it is possible to like add another meter behind the smart meter or the meter in your system, in your apartment, in your home, that is used for billing. So basically, you can use it as a control to check if the smart meter is measuring appropriately, or you can use it to get data for yourself. And there is quite a market for private power meters that come from devices that are very very experimental, like the ones here on the photo. They are from the Open Energy Monitor initiative. They come with a system where they are measuring basically the current, because it's interesting from an electric engineering perspective that you can measure the current through a wire without actually tapping to the wire, because a wire that is transporting some current generates a magnetic field, and you can measure that magnetic field by just enclosing it. So there's a possibility to measure this without tapping to the wire. So you can even use devices that are not designed to be safe at levels of grid power level of 230 volts, because you don't need to tap to this to 230 volts. But of course, you miss then the voltage information, which if the voltage is changing, which happens in our grid from time to time, then you get measurements that are not entirely correct. So instead of a smart meter that is doing exact measurements, we are using meters that are doing no exact measurements. But for the load disaggregation, the dynamics of the measurement, so how often do we get the measurement, is much more important than the accuracy. So while for a smart meter, it would be terrible if they would be off by 5% at some time, because that would affect your bill. And there is the requirement that they have to be much more exact than that. But for a meter that gives us the data for load disaggregation, this is fine. Therefore, there are these private power meters. There's also one meter we designed at our group as a prototype. So it's nothing that you can buy. It's also not CE certified because we didn't go for this process. But we looked into the practical experience, what would be necessary to build a smart meter. So we did it as a shield. Either we did two versions. One is a shield for the Raspberry Pi, and one is a shield for the Arduino as an add-on. And then this other part basically measures voltage and current and has a specific integrated circuit on it to do the power calculation in real time, so we don't get miscalculations here. Then provides the measurements to the microcontroller under the shield. And then the microcontroller, there are wireless interfaces. There are possibilities to store it on an SD card locally. So then we can get the data in a form that we can use it. And actually, those things are not so, if we only look at the parts cost, we are around 30 euros. Okay, including production costs and the assembly, I would say probably 90 euros. Would be absolutely doable to create and produce a smart meter just for load disaggregation at a reasonable price, because you get the measurement, and with the proper computer system, it would be possible to provide you the also the a proper interface about devices used, energy consumption used, which, as stated in the beginning, help you identifying the power-hungry devices and reducing or shifting the energy consumption. So we did some experiments with the smart meter. So it's you measure only once. That's why YOMO. This is just a name for it. We used the Raspberry Pi and an Arduino. So this was a setup where we had a Raspberry Pi as a web server and had the Arduino connected to the Raspberry Pi. In the newer versions, we just had the YOMO as a shield for the Raspberry Pi directly. And the advantage is also that Raspberry Pi is quite powerful, so you can run the routines to drive the measurements. You can run the load disaggregation algorithms there, and you can run the web server there that visualizes the data. So you would have one device that does everything. And with this approach, you also solve the privacy problem, because you don't give your data away to some company. You don't send it into some cloud. You analyze it locally. But this, of course, requires that you have an algorithm that runs well on a Raspberry Pi. So if you have an algorithm that is quite performance hungry, probably Raspberry Pi would not be sufficient. But if you have an algorithm that is so performance hungry that you need to do it in a cloud, then probably using this algorithm for an application where you want to reduce energy consumption might be the wrong choice. So for training the algorithms, I mentioned it already, you need data sets. And either you go now and do your own measurements, but that would mean you need not only one such system, but you need one measurement device for every appliance you have in your system. That would be quite an effort. And then also a good measurement, a good data set should also have measurements, I would say more than 1 year, just in order to account for all the seasons. Because if you compare the energy consumption of one system that is from January to another system that was measured in July, they might be very different, even if they are from the same household. Because energy consumption just so much depends on the seasons, on the temperature, on people being more at home, less at home, using more light, less light, more heating. So more than 1 year would be good. We would like to have a good measurement frequency. So here, as a rule of thumb, 1 second per measurement is good. More would be better. If it's less than every 10 seconds, I would say it becomes difficult to identify devices there. And then also there is then also we want to have the individual devices in the data set. And also there is a difference what is measured. Do we only have current measurements, like with the open energy meter? Do we have real power measurements? Do we also have the information about the reactive energy that is measured? So there are some differences from an electrical point of view, which we can use as additional data to feed our algorithms if we have them. So we need these data sets. And also it makes a difference which region they are from, because there are different devices. If you ever lived in the US for some time, or Canada, then you might have seen that their typical household devices are different. Like the washing machines, they are great. They are energy hungry, but they are great. It's loading from the top, and they are quite large. And so their other regions have other typical devices. And so we need the measurements from the proper region. There are some energy data sets available where you have measurements. For example, the first one from Switzerland was a resolution of 10 seconds, but it was only measured for 1 hour. So the second one from Vancouver, measurement duration 1 year, that's great. Resolution 1 minute, it could be faster. Duration is fine. Then some of these data sets, and also probably the most famous data set, or one of the earliest one, was the RAD-D data set. RAD-D is some acronym. Don't ask me exactly what the acronym means, but it just stuck because it's like a color and a D. And this RAD-D data set, it was only measured for a short duration, but it had a very high resolution of 15 kilohertz. So in order to find out what can you do if you would have a faster resolution, can be easily answered by taking the RAD-D data set and using all the samples, or downsample it to a low frequency and compare the results. And for that reason, the RAD-D was used a lot. And then another data set was available, the BLUE-D data set, also with high resolution for some duration. And then we had a project where we needed a data set, and we needed something for Austria and Italy, since it was an international project between those two countries. And we couldn't find any data set, so we decided to measure our own data set. And in the tradition of red D and blue D, we named it green D. So the green D data set is something we measured with the location Austria, Italy, where we measured it exactly to the requirements. So 1 year on 9 houses. As a disadvantage, only 9 different devices per house, which is not very realistic because typically we have more and 1 hertz resolution. So this was done with these measurement devices. Monachi, as you see here on the slide, this was the name of the project. And here is the list of the houses and the devices. As you see, we wired up things like coffee machines, washing machines, radio, TV, and all the stuff. And we relied on the availability of volunteers to have their house wired. And I was one of the volunteers. So my house was also measured. And I didn't get any information from the measurements because that might have changed my behavior. So I was only informed afterwards about the results. And when I was informed about the results, it was interesting because my assistants asked me, what do I think is the device that is consuming the most power in my home? And I was like, I don't know, the television set or some heating device, probably not the water cooker because it's very high power, but not so much used. And it was the PC. It was the PC because it's a PC which we typically use a couple of times during the day. We turn it on in the morning, and that time we had it set not to go to sleep mode. So it was on all day. And this was the main consumer of power. And after learning that, I just made the setting in the operating system that it just goes to sleep mode after a couple of minutes. And this totally changed the energy consumption within my system. But I had to learn from these measurements in order to know where I can save my energy, which brings us back to the original idea that by getting information at device level, we can save much more energy, because otherwise I would just study my energy bill, think, yeah, it would be better if I could reduce, but what should I do? Probably turn off the light. That would have been not helpful. So here are some examples of the power readings. So here you see the individual devices. The top one is a TV. Second one is an entertainment system. Washing machine. So here we see how a real washing machine looks like, with a heating cycle, then some smaller peaks here for the motor, and also times where it's waiting, and then heating again, and then again the motor. So the motor is much less than the heating. And yeah, different appliances that are available in this data set. So this data set is also available free for download. Of course, it doesn't contain any personal data or names. So you wouldn't know which house is mine. No, you know now, because you just have to look for the one with the computer as the maximum power consumer. And this can be used also for research. So if you want to try out some algorithms, you want to download NILDK, and you want to test it with some data set, then there are the things available to you, and you don't have to start everything anew. So, which brings me now to the summary. So this non-intrusive load monitoring approach is a resource-efficient way, because you only need 1 meter to detect appliance usage. And if you have appliance usage, we can give feedback to energy consumption and increase the awareness. And unfortunately, the current smart meters that have been rolled out successfully do not provide us the information with sufficient measurement frequency, which can be solved with a dedicated meter. And there are several open challenges, just to name another one. So apart from the technical things we already discussed, one would be, how would you present the data to the user in a way that it doesn't get boring. Because if you do something that is very technical, then probably it's read and looked upon like for 1 day or 1 week. But you need to find something that keeps the users interested in the results in the long term. So presenting the data, using computer graphics, using things to make it appealing is a challenge. And also you could think of gamification strategies, how to motivate energy savings, and also how to make this that it's sustainable longer than just one week after installation of the system, everything is back to normal. So there are some challenges, but in overall, this is an interesting approach that can help us reducing energy consumption. Just here, my references. If you want to look up some papers on this, and this ends my talk.